Hey everybody. Okay, so I'm going to be doing an exam run through of the 2023 October A2 Edexcel IAL paper. Okay, well, at least the sound works. Okay, in part one, I'm going to be doing the MCQ section. So it's going to be hopefully about 20 minutes just to run through the MCQs. Let's see if I can get all this. I need to present, share screen, entire. That one, please. Please, if you've got any questions, just throw them up on the chat. Happy to answer them. Okay. Now, I do want to point out here, everybody, I do not pretend to be flawless. I will make mistakes. And if I do, forgive me. It's just, I sit the papers as if I'm doing it. I do have the mark scheme ready to look at the end of the MCQ section, but I have not looked at the mark scheme as yet. So I will probably make mistakes. A2 is hard. I don't care what anyone says. A2 is tough. Okay, October 2023, Unit 4, rates, equilibrium, further organic. Okay, let's crack on, folks. So question number 1, which method would be most suitable for investigating the kinetics of this reaction? Okay, so it's an electrophilic addition reaction. I've got all gases. So the first one it says is calorimetry. Calorimetry, no, not going to be useful because the alkene is colorless. That is colorless. I'm just going to write it as Cl. Colorless, HCI is colorless, and iodo, that's gross. 2-methyl, 2-iodo-2-methyl propane is also colorless. So calorimetry is out of the question. No. Measure a change in volume. Possibly 2 moles. 2 moles of gas on the left, only 1 mole of gas on the right. So potentially possible. Measure a change in mass. No, because it's an addition reaction, so the total mass going in is equal to the mass going out. There's no byproducts. So that one's out of the question. Quenching with ice and followed by a titration with acid. No, the only thing that's here is an acid. We could quench it and titrate it with a base. That actually would probably be the best one for studying the kinetics of this one, but there's no base in the system, so you can't titrate with an acid. So the answer is going to be B. A very reasonable question to start off with. Okay, a methyl ester, methyl methanoate, plus sodium hydroxide to form the sodium methanoate and methanol. Again, same thing. Sorry, investigate the kinetics. Calorimetry, no. Again, all colorless, so not. Measure a change in volume. No, not really. You're adding a volume and it's all going to be aqueous, so that's not going to help me very much. A change in mass. No, again, everything goes in, comes out. Quenching with ice followed by a titration with acid. That one is very reasonable. That is put because there's a base now in the equation. So I could stop this reaction at a given point by cooling it with ice. It'll slow it right down. This is an alkali hydrolysis that they're doing. You can slow that down substantially in cold water. So D. They won't give you very good results. Hot bladder. I did this paper yesterday. And something calorimetry. Yeah, so, and chose calorimetry. Oh, yeah, fair enough. Definitely not calorimetry in this case. No colors anywhere. Calorimetry is about color. Yeah, calorimetry is about heat. But anyway, quenching with ice, that's very reasonable. I'd go for both of those two. That's my choice. So I'm going to take it hot blood of that. Colorimetry is not the right one. So that's, and I love the fact you put calorimetry. Lol. Okay, the equation for the reaction of bromate 5 ions with bromide ions in solution is given. Okay, it's an interesting one. The opposite of disproportionation. The rate equation for the reaction is as follows. The concentration of all the reactants are doubled. What factor will it increase? I love this question. So these are the orders. We've got an order 1, 1, and 2. So the total order is 4. Now, for those students who aren't sure, the total order is really needed for this exact question. If I double everything, you can do this stepwise, by the way, and it'll give you the answer, but the total order is really useful. So we're going to do double it times 2 to the power of the total order. You can only use this total order if you're doubling everyone. This is about everyone. Yeah, so just bear that in mind. So 2 to the power of 4, where's my calculator? It's going to be 16, but I like to do it on my calculator anyway. 2 to the power of 16. I'm going to go for D. Okay, next. This question is about chemical rates. I hate rate graphs. Okay, right. So just to remind students that there's 2 types of graphs in rates. We've got a rate graph, a genuine rate graph, and a genuine rate graph has time on the x. It always has time on the x and concentration on the right, either of reactants or products. And in this case, we're always talking about reactants. That's a deviation from GCSE, of course. So the reactions always come down. We have 3 rate graphs. If the order of Q is 0, it would be flat. If this one was T and Q and it was this is 0 order. If it was first order, it would do this. If it was second order, it would do that. Yeah, so that's second, first and second. So in this case, it's asked us for a 0 order graph. So we've got Q with time. This is a genuine rate graph, Q and time. So that's first order. So it's not that one. That's not 0. Rate and Q, they've been reversed. This is an incorrect graph in the first place. Then we've got another Q and time. Oh, this one works. There's my 0 order rate graph. Yeah, I'm going to go for C on this one. The other type of graph you always get is called a half-life graph. Let's just put half-life, lol. A half-life graph, and the half-life graphs are different. I still have learnt them as a 3, and you have your half-life graphs look like this. Your 0 order half-life graph. Got to be really careful because the problem is it's not that we have a straight line, we have a slight curve, and then you've got an extreme curve. Those are your half-life graphs. That is a curve, by the way. It's just a slow curve. So a 0 order. Now, by the way, just to give you some information, the half-lives is interesting because if you do the half-lives of these, the time gets shorter and shorter as you do it. There's the half-life 1, half-life 2, half-life 3. In the next one, because it's a curve, we actually get the half-life as remaining exactly the same because it's extending. Yeah. So in 0, the half-life shortens. First, the half-life remains the same. And in the second order, the half-life gets even more ridiculous because of such a ridiculous, it's such a ridiculous thing. So these get shorter. 0 gets shorter. First stays the same. And second gets longer. Just so you know, it's nice just to do a little bit of reminder of those graphs. Okay, the equation for a gas phase reaction is shown. The reaction is first order. When the initial pressure is 2 atmospheres, that's the same as concentration, by the way, the half-life is 20 seconds. Okay, and it's first order. What is the half-life of the reaction when the initial pressure of A is 4? Okay, so they've doubled the pressure. This is the same as doubling the concentration. And this is a half-life graph. So they've told me that it's first order, so the half-lives remain the same. Okay, so that one, it's nice to see that question. So 20 seconds, it won't change because it's first order. That's a neat question. I hated these graphs when I was at school. I found them really difficult, so I just compartmentalized them in my process of revision. I would practice doing the rate graphs, and then I would practice doing the half-life graphs, recognizing those little details. It's a really useful little practice to do. Okay, next. The graph shown is obtained for the activation energy. Yep, okay. We've seen this in kinetics. We do this a lot. This is how they link together the Arrhenius equation in kinetics. And we've got the activation energy, so they've given us the equation. Now, this is the reorganization of the Arrhenius equation. So we've got ln rate equals minus EA over times 1 over T gives me the constant. And plus the constant. This is Y equals MX plus C. Yeah, so the M is there. That's always the gradient. So it then says from the graph, the EA is equal to. Okay, so we know that the gradient equals minus EA over R. Notice, by the way, that the minus is actually in front of the whole thing. I don't tend to put it like that. I tend to actually do it as an independent. I actually tend to do it minus EA over R like that. But I'm not entirely sure what the maths rules are, associative rules. But the premise here is that it doesn't really make an awful lot of difference. So what I want to do is, in order for me to get a positive EA, the first thing I need to do is I need to flip its sign. So I need to make this positive. Now, if I make that positive, to do that, I must flip both sides. So this becomes a negative gradient, and this will become a positive, which means it vanishes from the equation. Yeah? The next thing is, now I put that into a bracket, and now I bring R over. So multiply both sides by R. So I get minus the gradient times by R will be equal to EA. Cool. So that's going to be C. Next. Gross. Okay, so the energy cycle for dissolving calcium chloride is shown. Okay, standard. This is like it's a Haber version of a Hess cycle, by the way, but actually it's the same premise. The enthalpy change of hydration for the calcium ion is, okay. So, that's really interesting. So just to explain what's going on here, we're going from 2 gaseous ions to 2 aqueous ions. This is the line that's doing that. Now, that line is technically a couple of pieces of data. So what we've actually got here is part of the line. I'll do this in different colors. I'll make it fatter too. Part of the line, I'll do highlighters. So a fraction of the line is going to be the calcium ion. I'll write this in red. So the calcium ion, so this is just this one. So this one going down here to form calcium 2 plus aqueous, they're telling us that there is minus 1650. Yeah. Then whatever this section here is going to be equal to 2 times the chloride ion hydration. So this forming aqueous from gas. Yeah. So I can now work out so it then says what's the enthalpy of the chloride ion. This makes total sense. So what they're now wanting is for me to find out from here, this is the start. This is the start, and this is the end of the step I'm looking for. And so in order to work out what that energy there is, I will start at the same point and end at the same point. But I'm going to go in this direction, then down here, then across here, and down here. Okay, I then get to use this as my cycle. So the first thing is that this arrow here that I have drawn on is from gas to aqueous, and we've been told it's negative. So I'm going to create an equation for this. The equation's going to be, so my delta H question mark, which is this one, is going to equal, and by the way, remember it's times 2, so you've got to remember to divide it by half. This one's going to be minus because it's going against me. I'm walking this way, but the arrow's going this way. So I'm going to have to say against me, brackets 1650. This one, skip across the top, this one's going with me. Look at the 2 arrows in the same direction. So with me, brackets minus 2258, close bracket. And then this one is with me as well. Look at the arrows pointing with me, brackets minus 120. Now, if I run that through my calculator exactly as I've written, minus brackets minus 1650, close brackets, plus brackets minus 2258, close brackets, plus brackets 120, close brackets. So I now get a value of minus 728. Now, most students would then just go, straight away, there's A. But don't forget, this is for 2 chloride ions, going from gas to 2 chloride aqueous. If I want a single one for the enthalpy of hydration, the heat energy change when 1 mole of chloride gaseous ions mixes with water to form 1 mole of aqueous chloride ions. And if you do that, you need to divide it by 2. So divide the answer by 2. Divide by 2 will give me minus 364. So I'm going to go for B. Oh, I'm going to switch to red there just for my answer. I always like my answers to be in red. Always nice. Cool. Next question. Why is the enthalpy change of hydration of a magnesium ion more exothermic than a calcium ion? Okay, so the explanation for this is the fact that a calcium ion is larger than a magnesium ion. Yeah, and it's simply down to the fact that it has an additional shell. Look at it in group 2. Beryllium, magnesium, calcium. Calcium's got 4 shells, whereas the magnesium only has 3. So what that means is when it forms the ion dipole attractions, when it forms these attractions to it, I'm going to be forming a far stronger bond with the magnesium. This bond here is far stronger than this one because the magnesium has a much higher charge density. It's smaller. Same charge, so you could just say the smaller ionic radius will lead to stronger ion dipole attractions or bonds to them if they're forming a complex. Magnesium has a larger radius? No. Magnesium ions form stronger ionic bonds? No. They're not ionic bonds. This is ion dipole attractions. Magnesium ions have a higher charge density. There's my answer. Magnesium is a higher first time, nothing to do with it. Ionization energy has got nothing to do with it. Okay, next, Kp. So we know that Kp is about gases. It's the whole point. Partial pressures, right? What that means is solids don't appear in the Kp. By the way, solids don't appear in Kc either, just so you're aware of it. So I can just ignore these guys from the Kp equation. So Kp is usually products for the partial pressure, brackets, NO2, raised to the power of 4, because it's in Kp and Kc. It's the stoichiometric ratios. Remember that. K, which is the rate constant, which I shouldn't start at that. Rate equals K, yeah, K, and then you have X to its order, yeah, and then multiplied by Y to its order, X and W, yeah? If it's a 0 order, then it vanishes from the rate equation. But those are orders. In Kc and Kp, it's not. We have products over reactants, but we know that these values here are no longer orders. These are the stoichiometric values. Yeah, so they're straight out of the equation, hence the 4. And then I'm going to put multiplied by partial pressure of oxygen raised to the power of 1. And by the way, you're not allowed to use square brackets. They're round brackets for Kp. Be careful. So, and there's no reactants because the reactants are a solid. So it vanishes. It's over 1, which is, well, it's just nothing. So the answer is D. Nice question, though. Like that. Next. Okay, conjugate acid-base pairs. Love it. Okay. Okay, so straight away, folks, we know that hydrochloric acid is a strong acid. Yeah, that's way more powerful. Thank you, sir. No problem, Farhan. Was this the one that you asked me to do? I couldn't remember, and I didn't go through my paper. I do apologize. I hope this is useful. I'm going to do the first half. I'm going to do the MCQ section first. I'm trying to explain each of them. So if you get stuck or you want a further explanation, just hit me up with a question. So we know that HCl is a strong acid. You've been dealing with that since year 7. And we know that all carboxylic acids are weak acids. What that means is the hydrochloric acid is going to protonate the carboxylic acid. It's going to transfer the proton to it. Hence, the Cl- and this one. Now, conjugate acid-base pairs are based on family and relationships. You can see that these guys are family. One is created from the other. And this one, in this case, is acting as the base, a proton acceptor. This must be forming the conjugate acid. Now, since this one is the acid, the Cl- is its conjugate base. So we can find those. The acid is HCl. These are all the same. That's fine. The base... Where's the base? Where's the base? Ooh, isn't that interesting? Conjugate base of acid 1. Oh, gross. So the conjugate base of acid 1 is the Cl-, so it's either C and D. And then acid 2, which now flips to this guy, has its conjugate base. Can I just point out, they've flipped it over. That's super weird, by the way. They're looking at it from that's a trick. They shouldn't do that. Yeah, but this one is the acid. And this is the conjugate base of acid 2. That's so stupid. Yeah, and that's correct. because it's going in the other. So the answer is D. But can I just point out, fundamentally, that question is flawed, and Edexcel are doing it just to try and trip you up. So D is the correct response, although we will check when I mark it. But it will be. At 100 degrees Celsius, pure water has a pH of 6, but at 25, it has a pH of 7. Yes, okay. Yeah, that's correct. This is because, so just to explain this, we know that water dissociates to form H plus and OH minus. Now, just to remind you guys, mexo-bendo, these are some of the most important, useful words I can teach you. Mexo means making bonds. Making bonds is exothermic. Yeah. And breaking bonds is endothermic. Now, we can see here from my diagram that this is the bond I'm breaking. So the forward direction is therefore endothermic. And the bottom one is exothermic when it makes a bond. That means if I raise the temperature, if I increase temp, I'm going to favor the endothermic reaction, shifting it in this direction. So it's going to be something like the dissociation of water is endothermic, so the concentration of H is lower at 100 degrees. Well, that doesn't make sense because the H plus concentration is going to increase at 100 degrees. That doesn't, is lower at 100. No, it's higher. So the dissociation of water is exothermic. This is incorrect, so we can ignore that. This one is correct, but the second statement is wrong. The dissociation of water is endothermic. Ding, ding, ding. So the concentration of hydrogen ions is higher at 100 degrees than 25. There's my answer. So there's C. Love it. And moving on. Okay. 4 beakers containing equal volumes of 4 solutions. Ew, gross. The pH of the 4 solutions was measured, which of the following gives the decreasing order? Ugh, that's gross. Okay. So what I will point out instantaneously here, I've got a strong base, sodium hydroxide, a weak base in ammonia. You guys should know from nitrogen chemistry in Unit 5, you should know that roughly the pH of ammonia is about 11. Yeah, and it's a useful thing to know that. It's about pH 11. It's a weak base. Yeah, sodium hydroxide is another strong base, and barium hydroxide is another strong base. And very soluble to boot, which is great. They're all, I don't have to consider solubility here. They're all very soluble. The only one that would have caused me trouble is recognizing that that's very soluble. Big iron, small iron, very soluble. Okay, so now I need to look at, so straight away, the one I believe would probably be last, because we've got decreasing. I want the highest, high pH to low pH. That's what I want. And the lowest here is going to be ammonia, which is going to be number 2. So it's going to probably be C and D straight off the bat, just based on that understanding of ammonia and the others being strong bases. So it's then need to look at which ones of these are going to be the strongest. So sodium hydroxide is very powerful, and it's 0. hang on, I'm just going to do this a bit more logically. Look at the concentration of this sodium hydroxide and look at this one. The top one is 10 times more dilute. What that means is this is a divide by 10. So the pH of that is going to be about 1 pH less. Yeah, it's going to be, so this one here is going to be the highest. Yeah, that one's going to be the highest out of those 2. Now, the problem is that barium hydroxide is dibasic. Notice that the dibase has got 2 AOHs per molecule. And this one, this concentration matches this concentration. So this one is going to be the strongest of those 2 because it's dibasic. It's a bit like having a concentration of 0.2 of the OH minus ions, right? So at that point, I'm going to say 4 is going to be the most basic. So 4 is going to be out of C and D. So I'm going 4 and 2 is probably going to give it. And just check the rest of them. This one's going to have the highest. Let's just put it at 14. Then sodium hydroxide is going to be probably 13. And then this one's 10 times less. That's probably going to be 12. And that one will probably be about 11. You could alternatively, by the way, pH equals the minus log of the base 10 concentration of H plus. Well, you can do that. We can just do the little clever 14 minus trick because it's just a neat trick to do this. So if I do the sodium hydroxide at the top on 0.0, I'm going to go minus log 10, and then I'm going to go 0.1. Oh, I've just done the wrong one. I'm going to change that to 0.01. 0.01 sorry, I've typed onto my calculator wrong. 0.01 equals, and I go 14 minus answer, I get a pH of 12. Lols, that's hilarious. Love that. Then we can do the sodium hydroxide, the other one. So this is now minus log to the base 10 of 0.1. That's going to give me 1. 14 minus answer gives me 13. That is actually correct. The barium hydroxide is double the OH minuses. Just to explain that a little bit further, barium hydroxide is dibasic. When it dissolves in water, I'm going to form one barium ion, but double the number of H pluses, which means the concentration that then doubles that one. Yeah, so I can do minus log to the base 10 of 0.2, and I go 14 minus answer, and I get 13.3 is what I'm getting for that one. 13.3. If you're wondering what I'm working out this value of pH, and then I'm doing 14 minus the pH to give me the OH. It's kind of like called POH, but I don't particularly like it as a trick. You shouldn't really use it, but it's useful in this regard. Okay. Next, I don't think I made that very clear. I apologize. If you want me to go over acid bases, I will. Okay. They've given me a beautiful set of reactions. PCl5 to make an acyl chloride. Reaction 1, good old lithium. We're taking a carboxylic acid and turning it back to a primary amine. So this is reduction. This is chlorination, technically. Chlorination. We're turning the carboxylic acid into an acyl chloride. This one is esterification, and this one is also esterification because they're both forming the ester. Nice ester too. Esterification. Neat. Which reagent is required for reaction number 1? The Edexcel are lovely on this one. You only need to have one. Lithium tetrahydridoaluminate. Yeah, I don't actually name. I actually prefer lithium aluminium hydride. But anyway, not that it matters. So, cool. I like it. Reaction 1 has a yield of 90%. What mass of 2-methylpropanoic acid is required to produce? I hate these calcs. It's horrible. And it has a yield of 9. That's how they make this A2, by the way. They add in this horrible yield trick. They do it at AS, by the way. It's kind of an AS question. They've even given us the MRs. That's kind of nice. So they've said reaction 1 has a yield of 90%. It's told us that the oic acid, which is there, has an, and they've said what mass of methylpropanoic acid, or what the mass of this, is required to produce this guy, 6.66 grams. Okay, now that's interesting, isn't it? Because the first thing I need to do is let's turn those grams into moles, so over 74. And they're even giving, by the way, they're not even giving correct MRs for A-level. Stupid idiots. Forgive me, Edexcel. 6.66 over 74. This gives me number of moles of 0.09 moles of it. Now we have to factor in the idea of the yield. Now, we can see that this reaction is actually a 1-to-1 ratio. I feel like you're almost making an assumption about it, but if you want to just see the equation, if I don't want to draw the whole thing out because it'll just be extensive, but just to kind of show you guys, if I've got ethanoic acid, let's just keep it really simple, and we turn that back using a reducing agent, which we always put in the equation as a H, to form methanol. Yeah, just to turn it back into the alcohol. What we realize is, in terms of carbons, it balances. In terms of oxygens, it doesn't balance, which means I'm going to need to add in water over here for the other. But then I just count my H's. I've got 4 H's on this side, and I've got 6, 7, 8, so I'm going to need 4 there. But what you realize is the people are like, why are you talking about this? Because the ratio between the oic and the ol is a 1-to-1. I don't want to rush this. I want to explain my thought process and explain how I'm knowing these things, but it's just useful. So this is a 1-to-1 ratio. So I would have needed 0.09 moles of that. assuming a 100% yield. But it's not a 100% yield. It's a 90% yield. What that means is this here is 90%. Well, what was 100% then? So if I take 0.09 and divide it by 90, it'll give me 1%. So divide by 90 times by 100. So I'm going to times that now by 100, and I get 0.1. This kind of makes sense. So what that now means is this: if this is the 90%, the 100% would have been 0.1, which means I would have needed 0.1 moles of this guy. Agreed? So so instead of using 0.9, that gives a 1-to-1 to a 90 yield. If I'd had 0.1 of it, if it had been 100%, I would have been made that, but it made us 90%, which will give us this. I hope that explains my logic there. Like, that's quite a bit of a complicated set of logic, but I hope you find that useful. Now I need to, of course, convert this back into grams. So number of moles is grams over rams, but I want grams in this case, so bring this over. Times by rams. So I just need to times this by 88. So I'm just going to go 0.1 times by 88, and I get a mass of 8.8 grams. So the answer is D. Nice. Next, which condition is essential for reaction 2? Which one was reaction 2? PCl5. Room temperature. Violent reaction at room temperature. Anhydrous. It also violently reacts with water. Sorry, I immediately, with PCl5, I immediately just have flashes in my head of, hey, it's done at room temperature. But it also needs to be done, and the more important one is, it needs to be anhydrous. PCl5. Do you know that every single school I have worked in has owned PCl5? And every time I've tried using it, it's already been dead because they've had it for so long, it reacts with water in the air over time and decomposes. It doesn't last very long. Reacts violently with water to form a HCl, by the way, and phosphoric acid, probably. I ought to know that one, actually. I could write the equation, but I don't want to get too lost in that. Reaction 3 and 4 produces the same ester. Yes, they do. What is the advantage of using reaction 4 to produce the ester in lab? Okay. Acyl chlorides are fast. These are really, really fast, but the problem is they're so fast, it's incredibly violent. It's so fast, it's not really controllable. It's non-reversible. This one is an OIC plus an ol. This one here, this is reversible. It is slow. This is reversible. These are the problems, by the way. It is slow, and it produces a low yield. Yeah, it's like a 30% yield, and that's if you do it well. Yeah, this is fast, 100% yield. 100% yield. But it does make HCl, which is a bad product, and it's also kind of uncontrollable. What have they given us? What is the advantage? It can be carried out at room temperature. This is correct. It requires a catalyst. No, it doesn't. The atom economy is higher. Atom economy is higher. Well, this one will spit out a byproduct of HCl. This one spits out a byproduct of water. MRs 18, 36.5. It's got a worse atom economy. It's got more MR coming out as waste. So it doesn't have a better atom economy. The hydrogen chloride is a product, but that's not an advantage, that's a disadvantage. So I'm going to pick A, but it's the first one of interest. I would say that you could potentially argue that HCl is a product so you can sell it. You can't sell water, but you could argue that you could sell the HCl. They do, I know they do as a byproduct, but I'd pick the first one being for labs, seems more reasonable. It's why I do it in lessons. Although I don't use PCl, I don't use acyl chlorides, I use anhydrides. Which diagram shows a repeating unit of a polymer formed by the polymerization of propane 1,3-diol and benzene 1,4-dicarboxylic acid? Okay. Right. So let's just break it up. Propane 1,2,3-diol. That is absolutely correct. That is correct. That's correct. This is not correct. That's pentanoic acid. This is correct. Yep, that's absolutely right. That fits. Okay, so the next thing is, what about the others? The next one is dicarboxylic acid. So let's do this one. You can see the benzene 1,4-dicarboxylate. This is correct. Ding, ding, ding. This is correct. Ding, ding, ding. I'll do them as ticks. Yes, yes. This one I've already eliminated, and yes, that is correct. Okay, the next part of the question is to identify 2 repeating units. So it's asked for 2 repeating units. This is a single repeat unit. This is 1.5 repeat units, which, by the way, is super weird. So let's just ignore that one. And I'm going to go for D. That seems much more, because it's got 2 sets, 2 sections of repeated. Unit number 1, unit number 2. Nice, neat question. Next, polymer waste can be disposed of by incineration. At a plant carrying out the process, polypropylene or waste gas was produced, thought to be either propane or carbon dioxide. This compound has a molecular ion peak, low resolution, yada, yada, yada. Okay, which one is the correct relative masses of the 2? Okay, well, I hope by now that you guys know that people know MRs. You start to pick them up, even at GCSE. Water weighs 18. The way I remember that, by the way, is because it's the year you stop drinking it. And carbon dioxide has a mass of 44. So straight away, I can pick up that chances are propane has a 44 as well, because that's why they're comparing them. C3H double it and add 2 versus carbon dioxide. 12. Okay, 12 times 3 plus 8 gives me 44. They both have rounded MRs of 44. This is why they're getting you to ask it. Look, they've given us a mass spectre 4dp, lol. So now we need to find out which one. So by the way, this immediately scraps out A and B, because we need to be similar to 44. So let's just pick one. Let's do propane. So no, carbon dioxide's easier, fewer atoms. Carbon is 12.000 plus 2 oxygens. So plus brackets 2 times 15.9949, close brackets, gives me 43.98. And there's my answer of D. Nice. That was a nice, easy question. I'll take that all day long. Is that the end of the multiple choice already? No, it's not. Okay, calculating an RF value. Nice. Oh, just to show you some of the tricks with RF values. RF values, we know that it's going to be dot distance over solvent distance. That's it. So the dot from the baseline, so we're working out X from here to the middle of the dot. Yeah, and from the baseline to the solvent front, work out those distances. Well, if it was exactly halfway, it would be 0.5. It's below that. So A and B are possible, but C and D are not. It's nice just to do that, eliminate some of them. Now, I'm going to say, I'd probably say it looks like 3.8 to me by sight, but, you know, it's always good to show you're working for this. So I'm just going to line this up and go to the dot and go 1, 2, 3, 4, dead on 5. Yeah, so that's 5. And then this one, if that's 5, 6, 7, 8, 9, 10, 11, 12, 13.3. So 5 over 13.3 gives me 5 over 13.3 gives me 0.376. So it rounds to 3.8. Nice. Make my ruler vanish. Okay, next. Okay. So yeah, I sort of thought this was coming. This is sort of talking about how chromatography works. So this is always to do with the stationary phase and mobile phase and their affinity for them. Yeah, so in this case, we're comparing, so Y traveled further than X. We need to say Y has a lower affinity for the stationary and higher for mobile. Okay, attraction between Y and the stationary. Y is less attracted than X. So is weaker than the attraction of X in the stationary. There's C. Because this one is stronger attraction. Nope, because it wouldn't have traveled as far. Stronger attraction. Nope, weaker and weaker. But this one is weaker than the attraction between X and the stationary. Oh, how do these? Oh, they're the same. Okay, so C and D are possible. It's not, I'm talking about not reading it. C and D are possible. Right, now I need to realize what about the mobile phase? Y has a greater affinity for the mobile than X. There's a stronger attraction between X and the mobile. The attraction between Y and the mobile is stronger than between, I'm going to go with C for now, but I'm going to read the second one, is weaker than the attraction. Oh, okay. So Y is stronger because it's traveled further. So just to try and explain what's going on here, if you imagine, I always imagine lying it down. I know it seems a strange thing, this, and having your water is going to soak up through the paper like this. Yeah, and here's your dot. The dot's on the paper at the point. The water level, which was below that line, starts to soak up, and the water picks up the dot. Now, if the green dot has a high affinity for the mobile phase, then it will soak up, the water will carry it until it gets to the point where its attraction for the stationary phase, the paper, sucks it back down. That's the way I always think about it in my head. I hope that's helpful. That brings me to the end of multiple choice. Okay, now I have to mark the thing. So what's the best way for me to do this? Hang on a sec. Okay, I'm going to separate this all the way off. Separate that one. I'm going to split this screen of mine into that one there. Right. Make that vanish. Multiple choice. Can I zoom out on that? Yes, I can. Right, I need that one to go full screen. Okay, right to the top. Let's see if I get them all right. I would never expect to get all multiple choice right, by the way, on an A2 paper. Multiple choice are hard. This one was relatively straightforward from my experience of them, but we'll see. So question number one, I'm going to mark this in green. No, I'll mark it in, yeah, green, why not? Okay, number one was B, correct. Number two, D, correct. Sorry, 1B, apologies. Number two is D as well. I never look at any patterns, by the way. I always avoid them. These graphs are horrible. Oh, the only correct answer is A. I've made a mistake. What did I do? Oh, there you go. I've made a mistake, folks. Oh, what the heck did I do that? First order. What did I do? Zero order. Rate changes. Okay, guys, there's my mistake. So, oh, darn it. So easy. I hate rate graphs. So, this is incorrect. I need to add more detail on this. The reason being is I've suddenly realized that in zero order, the concentration of Q does change. Oh, that's a nightmare. I've got them. Oh, that's really irritating. Time and Q. Right. Okay, I've made a mistake because this isn't actually I've done the wrong thing. This is time versus concentration. This isn't what they want by the means of a rate graph. Okay, just to explain, this is Q against time. Q's concentration against time. I'm so sorry, folks. But what you'll notice is the word rate isn't there. An actual rate graph I've gone and made the mistake. This is rate. I'm so sorry. This is rate. Yeah. And what this is, oh, darn it. And this is concentration. I've made such a faff of this. I apologize, folks. Ignore me. I've made a mess of it. This is Q. Yeah. And this is rate. And what we realize is what this is saying, what these rate graphs are actually saying, I call them rate graphs because they've got the word rate in them. As Q increases its concentration, the rate remains the same. As Q's concentration decreases, the rate decreases in a linear fashion, first order. As Q's concentration decreases, the rate decreases as well. Yeah, but this one is doing it over time and how it changes. This is a nightmare. Should have caught that. So just to explain what's happening here, the answer is A. There you go. I told you I'd make a mistake. I don't pretend to be flawless. Please don't shout at me. The reason being is as time progresses, the question is which graph is zero order. As time progresses, Q is decreasing in a linear fashion. This is to be expected. That's what you would have. Whereas if this one was the rate in first, hang on a sec, the rate one is still going to be okay for, oh, 0. Damn it. This is, this graph here is for first order. RTFQ, it's killing me. This is my absolute standard first order. Yeah, but they're looking for 0. This one makes sense. As time progresses, Q is used up. But what we realize is this it's a half-life graph? Oh, it's a really bizarre link to a half-life graph. Oh, I'm so sorry, folks. I apologize. This is a weird half-life graph that doesn't exist. That means it doesn't ever change, which means it's a catalyst, if anything. Yeah, this one's as Q concentration increase. This is a standard rate one. You could argue this is a first order. As I double Q, the rate doubles. This is also a first. It's this graph here in reverse, rather than looking at it decreasing. They're looking at the way it increases. That we're looking at, but it's not. This is looking at a product. We don't do that. Just point out. I'm so sorry, folks. I don't expect to be perfect. Next question, B. At least I got the next one right. Oh, I hate making mistakes. It makes me feel bad. C, correct. Next one is B. B is correct. Ah, sorry. B is correct. Part B, charge density. There we go. C, correct. Oh, rate graphs. Practice them, folks. Practice them. 6, I don't pretend to be perfect. This question I hated because the question was fundamentally made up by Edexcel. They've flipped all kinds of weird language. Shouldn't do it. Naughty Edexcel. C, correct. D, that was a tricky one. Took me a little bit of time to solve that one. Lithium tetrahydroaluminate. Correct. 8.8 grams. Yes, thank you. Anhydrous is the only condition, but also room temperature, but anhydrous is more important. Next one, D, is A carried out at room temperature? Yeah, okay. It's nice to have that confirmed. D, 2 repeating units. Nice. And D, a nice easy ending. That one, am I done? Nope. RF, 0.38, winner. And C. I don't pretend to be perfect. Right, guys, I don't think there's any more, right? Nope. I will have a go at section B then. I have to go in. Oh, didn't turn my laptop on. My power. Let's go back to my YouTube channel and I want to go back to nope, that one, this one, and go this one, please. Hello, 48 minutes. I'm so sorry I got the graph question one. Rates graphs are horrible, especially the way they phrase them. So I hope you found this useful, folks. I will do part B probably tomorrow. Guys, have a nice rest of your day. See ya.